Okay, so the next thing we've got to do with these covalent molecules is actually start naming them. And luckily for all of us, the naming system isn't that dissimilar to what you've already encountered with ionic compounds. The difference is, though, interestingly, that we use prefixes to identify the number of each atom. Again, none of this is going to make perfect sense to you until I give you some examples. So here they go. So for example, if I'm talking about this compound here, let me get out my handy dandy felt tip pen. I'm going to use red this time. Aren't I a radical? So if I look at this compound here, carbon monoxide, why is it carbon monoxide? Because I've got carbon with one oxygen only. So it's mono being one, of course. This compound here is CO2. There's two oxygens, therefore it's carbon dioxide. Notice that the suffix of the word here, oxygen, changes to "ide", which is the same as before with the ionic compounds. Here we've got sulfur trifluoride, and here we've got carbon tetrafluoride. How do you know which one of these you write first? Well, generally the element that's closest to the left of the periodic table is the one that's written first. Alright, so how do you name a compound like this? Well, you've got to remember your suffixes. So it's nitrogen, there's two of them. So it's di-nitrogen, and there's four oxygens. 4 is tetra. So it's dinitrogen tetraoxide. Alright, now we're going to start having a bit of a think about the shapes of these molecules that are formed via covalent bonds. Now, if you recall back first of all to ionic compounds, there are no real shapes there other than the things arrange themselves in this regular lattice structure. Now, this isn't the case for covalent compounds. They form molecules and they can form quite complex shapes. You might think, well, who cares what the shapes are? But basically all of biology is dominated by molecular shapes. And that includes things like drugs that are used for treating particular diseases, etc. They're all reliant on shapes. So of course people are extremely interested in the shapes of molecules. So how do we work out what these shapes are? Well, we use this horrendously complex sounding idea or theory called Valence Shell Electron pair repulsion model. It sounds appalling, but it's actually not as bad as you first think. Best way to do it is kind of to get into it, really. Okay, let's start with an example. Let's look at beryllium. Okay, now the way in which you, there it is. The way in which you think about the shape of something is first of all consider an element. Let's consider beryllium. It's got a valence of 2 and it can form a compound like beryllium hydride. So what I'll do is I'll just write beryllium, Be in there, and I'll write a hydrogen here, and I'll write a hydrogen here. Now, the shape that that particular molecule forms is exactly as it's written here in this diagram. It's a linear shape. How do we account for that? What theory do we use? Well, it's pretty simple actually. If you recall here, these lines represent covalent bonds. And really, if you look at this and think of it another way, what you've got is you've got electron clouds here. So these are electrons in here whizzing around. I'm going to draw another electron cloud here, and these guys are whizzing around. Now, you all know what the charge on electrons is, and it's -1. So when I look at this, what I see is this is a big fuzz of negative charge in here. There's a big fuzz of negative charge in here. And so you could imagine that if the molecule kind of moved up this way and this way, these two negative charges on these arms here would get closer together. It's a bit like imagining you were holding two magnets here, and as you brought the magnets this way closer together, this is your head here, this is your back, this is your front, like this. There's your back, there's your front. As you're holding those magnets and you bring them closer together, they'll repel one another. And of course they'll repel one another back in this direction to minimize the force of repulsion between those two clouds of covalent bonds there. And of course the same thing applies this way. If this was now your back and this was your front, and these are your arms here, and you're holding two magnets, and you start bringing them together in this direction, they'll try to repel one another. This is of course assuming that this is north here, right? Of course it's the other way around, they'd attract one another, but it wouldn't make my explanation any better, that's for certain. Okay, so what does this mean? Well, it means that for this particular molecule, its most stable shape is going to be when the distance between these two electron clouds is at a maximum, and therefore that's going to be when it's linear. Go back to here. That's what all this means. Valence shell electron pair repulsion model means that these electrons in these clouds here try to repel one another and get as far apart from one another as possible. It's that simple. And it makes perfect sense that a molecule like this would be linear to try and maximize the distance between those two clouds. Alright, now let's look at boron. Boron's got 3 valence electrons. Let's think about the shape that boron hydride would form. That's the shape there. You might think, well, why is that? Well, ask yourself, given I've got a cloud of electrons here, and a cloud of electrons here, and a cloud of electrons here, what's the maximum distance that these guys can get away from one another? There. What's this maximum distance? Well, if these two guys tried to push even further apart, this one would get closer to this one, so that's not going to work. So they have to kind of even each other out here. Now, if this is in a plane, which it is, right, that's a circle. In other words, that whole thing is 360 degrees. So there's 3 angles here. 1, 2, 3. So the angle between these things is 120 degrees. So I know for a fact that angle there, and I don't remember it, I just know it because it makes perfect sense. That angle there, there, and there is 120 degrees. Now we have to use some moniker to try and explain what this shape is, rather than every time going through the laborious process of saying, well, the molecule's sitting on a plane and the angle between each of the bits within that molecule is 120 degrees. So we use a term like planar because it is on a plane, and you can see it's triangular, right? So some people call it triagonal coplanar, and some people call it trigonal coplanar, but it's the same thing and it makes perfect sense. Now we come to carbon. We're going to use the same idea, but it's going to be a little bit different. I'll just point out what I mean here. Right, this is the structure here. It's actually, now we're moving away from a planar structure because we only had one thing in the middle and 3 points on the outside. We've now got one thing in the middle and 4 points on the outside. And the most efficient structure to maximize the distance between these bonds here is no longer on a plane, it's actually in 3 dimensions. So this thing is in 3 dimensions. And because it's in 3 dimensions, you just simply can't take 360 degrees and divide it by 4 for the number of bonds here. The bond angle here isn't 120 because the total angles here are not 360. So the bottom line here is when you work out mathematically what the bond angles are, they come out to be about 109 degrees. Which is what I've got there, right? But it's in note that it's in 3 dimensions. Now again, we need some sort of word to explain what this particular shape is, rather than laboriously going through the explanation that the thing's in 3 dimensions and the bond angle's 109 degrees. So this particular shape, mathematically, is referred to as a tetrahedron. So there it is there. Okay, now let's go and have a look at nitrogen. Now nitrogen looks kind of weird here. The best way to explain it is to actually think about what carbon looks like. Now if I go back here and look at carbon, can you see I've got a central carbon and then there's my hydrogens there, because I'm considering methane in this instance, CH4. Nitrogen's actually not that dissimilar, except this bit here, this atom is missing. Okay, let's go back to nitrogen. Right, nitrogen's got an atom in a sense missing here. Why? Because its valence is 3. If I was to draw the Lewis dot structure of nitrogen, we got 1, 2, 3, 4, 5 like this, and say it's combining with hydrogen. I'll use an electron from hydrogen. I'll use an X instead so you can see the difference between them. There's 1 hydrogen, 2 hydrogens, 3 hydrogens, like that. If you count up the number of electrons here for nitrogen, from its perspective it's happy, right? 2, 4, 6, 8. For hydrogen it's happy, 2, 2, 2. But it's got this pair of electrons here. Why are they in a pair? Because electrons hate going around as singles, so they pair up. But nitrogen's got the right noble gas configuration. It certainly doesn't want to bond with anything else. So that's why there's an atom so-called missing there in comparison to carbon, because it certainly doesn't want one. So when you look over here, this A here then's nitrogen in the middle, this B is a hydrogen, this B is a hydrogen, this B is a hydrogen, and here's my 2 electrons sitting here, my non-bonding electron pair. Now, can you see that the shape of this thing is still a tetrahedron, just like carbon, but it's got this weird electron non-bonding pair sticking up here. So if I asked you before anything else, what the angle would be between these bonds here, your response should be 109 degrees, because that's what it is with methane. It's 109 degrees. Okay? However, because of this issue with this non-bonding pair, things are a little bit different. If you can imagine here that the angle is originally 109, and between here 109 as well, and at the back it's 109, all good. But because this electron pair here isn't drawn out by bonding with another atom, it tends to kind of push harder in this direction than these electron pairs do. So these push harder. So they kind of squash these bonds up a bit. So instead of being 109, these actually get squashed up to about 107 degrees. And because this structure is different to that tetrahedral structure, it's given a different name. It's called pyramidal. So there you have it. There's the structure of all of the nitrogen compounds. Now it doesn't matter, of course, whether you've got hydrogen here, carbon or whatever, you're going to get the same kinds of structures. Alright, I'm going to leave it there and then I will go on to part 3.